Are you ready? 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 Shout! Shout! Let it all out. These are the things I can do without. Come on. I'm talking to you, so come on. Now I know.
Well, good morning everyone. Today we are going to be doing a project where we're installing a couple of zirconia oxide oxygen transmitters onto a couple of heaters. Now the purpose of this is that the current system that analyzers are in situ. Whenever you say in situ, that means it has no, it's not pulling the sample down and then measuring, it's in it. It's inside the vessel. So, but at this point in time, they keep burning up the probes and having to replace them on these Zirconia Oxide O2 transmitters, which is kind of odd because those things have to run at like 800 degrees Celsius just to function. But anyway, I guess the heater's getting way hotter than that and cracking them. So what we're going to do is we're going to put in an extractive type, but still in situ. It's hard to explain, but not really. What we're going to do is, have you ever heard of an aspirator or an eductor? If you've ever had a sandblaster, the big thing, and you put your arm in the gloves and you pick up the thing, and when you push down on the pedal, it starts making air go through this thing. When the air goes through it, it actually makes a suction on the other side. Well, that's exactly what this is. It's an eductor. And this eductor, we're going to put instrument air on it. As the instrument air is being pushed through here, it's going to pull a suction on this part. This part will go to here. The transmitter right here will bolt up here. Now on this right here, we're going to put a probe, a long probe, and it screws into here and goes into the heater. So the sample will be getting pulled. This one's broke. We're going to have to get another one, but it's going to be being pulled through this probe into here. All right, so we're pulling the sample in. It's going to go across the analyzer cell, and then it's going to spit it back out, and then it's going to come out there, right there, and then spit it back out into the heater. So pulling in fresh sample from deep inside of the heater, pull it through, go across the zirconia oxide analyzer, and then push it back out. So to explain the zirconia oxide O2, let's do a little, I guess we're going to have to do a little chemistry, huh? Okay. Okay, so if we're taking a look at a periodic table, and we know that hydrogen is our lightest, tiniest guy on the planet, and then it comes right after that with helium, number 1 and number 2, and carbon is what our entire periodic table is based on, which is carbon 12. But if we look over here at oxygen, so oxygen is got an atomic weight of 16, okay? Number 8 on the periodic table, 16. Are we ready for this? Here we go. We're going to be explaining the heater and everything that we're doing for connections, but right now we're going to take a look at the chemistry. The chemistry said oxygen is number 8 on the periodic table. So if we're saying that we have 8 protons, 8 neutrons, and then we're going to have 8 electrons, positive, negative, so we're going to be doing our breakdown here. So what's the first rule of Fight Club? Never talk about Fight Club. But in this case, first ring needs to, wants to, has to have to. So we got our nucleus with 8 protons, 8 neutrons, and that's going to make our weight of 16 for our atomic weight on the periodic table. First ring, electrons, wants to, needs to, has to. We have 8 electrons. So 1, 2, now we have to jump to our second ring. 3, 4, 5, 6, 7, 8. The rule for the second ring is we want 8, need 8, have to have 8. Want 8, need 8, have to have 8. Second rule of Fight Club. Gotta have it. So 1, 2, 3, 4, 5, 6. We have a valence of 2. We need 2 to make this rule okay. Make everybody happy, we've got to have 2 electrons to fill that ring. So what happens is oxygen is going to run into another oxygen, and they're going to and do some sharing. This is what happens whenever 2 oxygens meet and we become O2. So we have to solve our rules. The first rule was you have to have 2 electrons on your first ring, and you can't have any more than 2 on your first ring, and then you have to jump out. Second ring has to have 8. Needs 8, wants 8. And in this case, you had 1, 2, 3, 4, 5, 6. So it needs 2 more. It has a valence of 2. And it needs to solve that. This oxygen has a valence of 2. So if you bring this oxygen to this oxygen and they form, now we have 1, 2, 3, 4, 5, 6, 7, 8. Solve the rule. O2 combining together solves the rule, and everybody's happy and wonderful and everything's great in this land. What happens if oxygen runs into some hydrogens to cover up these? If you had your oxygen running around here, first rule 2, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. But we don't have 8 in this outer ring. 1, 2, 3, 4, 5, 6. We still need a valence of 2. And hydrogen, who's running around out there with 1 electron, needing 1 more electron, if that guy comes over and says, I'll share my electron, and you share your electron right there, and then same thing here, I'll give you my electron, and you'll share that electron, nucleus, nucleus. What did we just create? Mickey Mouse is the correct answer. Mickey Mouse. No. Zirconia Oxide O2 is based on the principle that we are going to split these oxygens molecules from each other. So one O will split from the other O, and we'll actually have 2 O's instead of O2. And then they're going to actually maneuver their way through a superheated zirconia oxide piece of metal where we have reference gas on the other side. And as they make their way through it, it creates this electrical charge. And when they recombine, that's how we're going to get our measurement, which is reference gas versus our actual whatever we're measuring. It's extremely hard to explain, but just understand that we're splitting molecules and putting them back together, and it creates an electrical charge on how we're doing this, and you have to have reference gas. Why are we even measuring for oxygen on this? So you have a heater, you got fire, you're blowing this fire up into here, and you're using the O2 measurement to control your dampeners down here. You want to get that just right oxygen flow coming through here. Your fire triangle, you have to have, fuel, oxygen, and then a spark. Well, then you optimize the fire, or otherwise you'll burn this sucker up. People burn heaters up all the time. It happens quite often. So you're wanting to control your oxygen content flowing through this heater to optimize your burn and get the absolute best thing out of it. In this case, I'm putting everything together. We're gonna have a 0 bottle, stand bottle. We're gonna mount all of these guys. Instrument air, we're gonna have instrument air coming up here for doing our eductor, aspirator, sucking the sample up through. Sample probe going off into the stack on the heater. This sucker's hot, so we don't plan on taking it down whenever we do this either. So it's gonna be hot. It's gonna be really hot. So yeah. The only thing that would make this even better is if we had a CO monitor to go with the O2, and you could really do some advanced process controls. Okay, so here is our transmitter. We're gonna have our reference gas, and then cow gas will go in here. Then you have your exhaust for your reference gas exhausting. This is down inside of there. There's a thermocouple down in there. And because it's such superheated, it has to be like you can't be a type J, K, or E or something like that. You have to be an S or a T. And when you're an S or a T, that metal is, it's super expensive metal. What is that? I can't remember right this second on the metal for S and T's, but it's platinum. Okay, it's platinum. Anywho, here is our cell that we're having down in here. This is basically just a filter, probably about a 50 micron filter. We're going to be pulling our sample in through here for doing our oxygen measurement, and I will be putting all this guy back together.